All right, my friends, just a quick lesson about what's called Euler's Method. Euler's Method is a series of tangent line approximations used to solve a differential equation that we wouldn't be able to solve using the methods that we know so far, okay? So one thing I'd like to do before we get started on Euler's method is refer to something we did learn earlier that people oftentimes get confused for Euler's method. So first thing I'm going to do in this lesson is compare Newton's method, which we did earlier in the year, to Euler's method, which is different, and what we'll do in this lesson. Okay, Newton's method is what we did earlier in the year, and I'm not going to rehash the whole thing. I'm just going to give a brief review of what it was, and then Euler's method is what this lesson will be about, okay? Both are a series of tangent line approximations, so they have that in common. But for Newton's method, the idea behind Newton's method, I'll just draw you a picture real quick. Newton's method was used if you are given a function f, and for whatever reason finding the zeros of the function or the x-intercepts of the function, if that was impossible to do using algebraic methods that we know and love, then the idea was that you could start with a guess, kind of a ballpark guess as to what it is. You could kind of try to get close and then plug that guess in and then find the equation of the tangent line to the function, and then find the x-intercept of that line, knowing that you're probably pretty close to the real x-intercept. And then if you didn't feel like you had enough accuracy, you could just keep doing that process. So then this would become your second guess, and then you could plug that into the equation, find the equation of the tangent line. And you can see, even by round 2, I would be pretty darn close to the real x-intercept there. And so that was Newton's method, okay? So just a quick summary as to what you would be given for Newton's method. So for Newton's method, you would have been given the rule for f of x. Okay? And then it was a series of tangent line approximations used to estimate the value, I'll say value or values, of the zeros or roots of the function. Okay, so that is something that we did a long time ago. I've never seen them put Newton's method on an AP exam, but I have seen them put Euler's method on the AP exam, and it is on the list of topics that they might test you over on your test this year. So let's talk about Euler's method. Euler's method, they would actually not give you the original function rule. Instead, they would give you a differential equation that you cannot solve by separating variables. They'll purposely give you a differential equation that you can't solve, okay? So here's the story behind Euler's method. So for Euler's method, you will not be given the rule for f of x. You will be given the rule for like dy dx or f prime. And you'll also be given an initial value. an initial value of the original function without them giving you the function rule. And then Euler's method is a series of tangent line approximations to estimate any y value for the graph of f. Okay, so I'm going to try to draw a picture of what happens in Euler's method. Let's say that the function rule f, which we wouldn't be given the rule for it, but like let's say that it looks like this. I know I always draw function rules to look like that. It's a glitch. I don't know. So let's say that this is what the function rule actually looks like, even though we wouldn't especially know that. Here's what we would know. We would be given an initial value. So for example, maybe they say something like f of, like, let's say they tell you like this point right here. They're like, okay, f of 5 is 2. So an example, I'll just say example. And they say, okay, f of 5 is 2. So that would be what the initial value looks like. And then you would have a rule for dy dx. Well, what does dy dx tell you about a graph? It tells you the slope of the tangent lines, right? So if they tell you f of 5 is 2, and then they're like, okay, we'll use the rule for the derivative, and I'll do an example in a second to kind of take some mystery out here. But if they say use the rule for the derivative to figure out what f of 9 is, I don't know, 9 or something, and they tell you to use what's called a step size of 2. So that would mean you're going to go from 5 to 7 to 9 if they say step size of 2. So basically what you do is you would use the initial condition and you'd use whatever rule they give you for dy dx, and you'd figure out the equation of the tangent line at the initial value there. And then you won't have the original function, so then what you're going to do is increase your original value 5 here by whatever they say the step size is, so then you'd go up to 7, and then what you'll do there is you'll plug 7 into your first tangent line equation and get a y value, and then you're going to take the 7 and whatever y value you get, and you're going to plug it into the dy dx function, because dy dx will at least tell you what the slope of the tangent line would have been. So then your next tangent line that you tangent line, because it won't quite be on the graph, but it would at least be kind of following the shape of the curve because you keep using the derivative function that you were given. And then from there, since that was the quote tangent line at 7, then you'd increase 7 by whatever they say the step size is. So like, let's say, I'll just say step size increase in x by 2 or something. Then you go from 7 to 9, and then you'd plug 9 into your last tangent line, and then whatever number you get, you'd say that's approximately equal to the actual function rule. So you can see based on my picture that the only thing that's perfectly accurate is the first equation of the tangent line, and then we keep having the slope perfect, but you can see you're a little off of like what the real graph would have been. To get more accuracy, you could use really tiny step sizes, like a step size of 1/100th that would make your tangent lines hug the curve tighter. But that's where we would probably stop doing it by hand and start making a calculator or a computer do it. But for the AP exam, they usually use really big step sizes and not a lot of iterations of the process because they're just checking to see if you understand the concept. Okay, so let's give you an example because it's pretty possible that right now you're swimming in theory and wondering just kind of like, hey, Mizzy, can you just show me how to do one? So here you go. Example 1, let's say I say given, oops, you won't be given F. Okay, given dy dx is equal to x plus y and y equaling F, actually, sorry, and let's just say, and F of, let's just use this, let's say F of 5 is 2. Use Euler's method, U-L-E-R apostrophe S, Euler's method, and with what's called a step size of, let's say we're doing a step size of 1 this time, to approximate f of 7. Okay, so for this problem, notice that dy dx, this is not the kind of thing that we could solve by separating variables, and they'll do that on purpose. They don't want you to solve it by separating variables. They want you to use this numerical approximation method to show that you can do it, okay? So the first thing that we would do is we would find, I'll just call this round 1. What you do is you find the equation of the tangent line at the initial condition. So find equation of tangent line at initial condition, which would be 5, 2. Okay? So how are we going to do that? The first thing you need to do is get what the slope of the tangent line is. So dy dx at 5, 2 would be simply 5 plus 2, which would be 7. Okay, so a very steep tangent line there. So then the equation of the tangent line would be y minus 2 equals 7 times x minus 5. Then from there, I always isolate y. I don't think it's going to be worth your time to distribute the 7 in. I would just leave it like that. And then next what you're going to do is use the step size of whatever they give you. In this case, it was 1. And then you're going to increase the original x value by 1, and then you're going to plug that number in. So we would plug a 6 in to this tangent line. So you'd figure out, well, what is y when x is 6? So 6 minus 5 is 1, so you just end up with 2 plus 7, or 9. So y when x equals 6 would be 9. So that would be round 1 of Euler's method. So at this point, essentially, you have found, I'll change the numbers here a little bit, you found the equation of the first tangent line, and then you plugged 6 into it. So now you would know the coordinates of that point right there would essentially be 6, 9. Okay? So round 2, what you're going to do for round 2 is find the equation of the, I'm going to put quotes around this because it is not essentially tangent really, because it doesn't touch the curve, but it would have the same slope of the curve. The tangent line at this point that we just got, 6, 9. So to do that, we're going to take the rule for dy dx, and we're going to put those numbers in there. So, so dy dx, if you put 6 here and then the 9 here, you'd end up with 15. Okay. So now the equation of this, quote, tangent line would be y minus 9 equals 15 times x minus 6. Isolating y would give you 9 plus 15 times x minus 6. And then, so this is that that second, so this is kind of like this line right here, that second one. And so now you're going to increase 6 by 1 because they said the step size was 1. And then you're just going to plug that next number into this line, knowing that you're probably not getting the exact thing, but you're getting an approximation. So you're going to take y and you're going to plug 7 into it. And so you'd end up with 9 plus 15, which is 24. And they wanted us to approximate f of 7. And so we wouldn't say f of 7 is exactly 24, but we could say f of 7 is approximately 24 using Euler's method. There we go. Okay. I think I'm going to give you maybe one more example like this, and then we're going to show how to do a multiple choice problem that we'd previously had you skip because we hadn't taught this lesson yet. So example 2. Sorry, just a second. I just realized I need to do something. Okay. Okay, so given dy dx equals, let's say, y minus x squared, and f of 0 equals, let's say, 3. Let's have you use Euler's method. With a step size of, let's say, 1/2. Is that going to be super gross? Oh, well, whatever, we can handle it. To approximate, let's say, f of 1. Okay, this is very similar to the example we just did.